In this video we're going to multiply together two 32-bit floating point binary numbers. Now the first number is going to be minus 0.7, and this here is the approximation to 0.7 using this 32-bit binary floating point number. And you can see the repetition here, 00110011, and we cut it off at 0.32 and we use this as our approximation. The second number we're going to use for the multiplication is 492.75, and this number has an exact floating point binary representation, and this is the floating point binary number here. So if you like, you can open up the file that's in the resources section and you can run up the binary to decimal converter and you can put these values in. So whenever we've multiplied these two numbers together, we should get the following number: minus 344.925. Now, as I said, this is still going to be an approximation, and you can see how close it's got, 9249877929969, and this is the answer here. So what we'll do is we'll multiply the two floating point numbers together and we'll check and see that we do actually get this answer. Let's say we want to multiply together these two numbers, 5 times 10 to the 2 and 3 times 10 to the 3. Well, 5 times 10 to the 2 is 5 times 100, 3 times 10 to the 3 is 3 times 1000. So that's going to be 500 times 3000, which would give you 150,000. Now we can write that as 15 times 10 to the 5. So that's equivalent to saying we take the 5 times the 3, which gives us the 15, and we take the 2 plus the 3, which gives us 5. So we multiply together these numbers, which we could call the Mantises, and we add together the exponents. Now we could normalize this as well and write this as 1.5 times 10 to the 6. So in decimal, in order to multiply together a number x with a number y, it's going to equal the mantissa of x times the mantissa of y times 10 to the power of the exponent of x plus the exponent of y. Now the same thing's going to happen whenever we're using the base 2. We just change the number 10 to a number 2. So x times y is going to be given by the multiplication of the Mantisses and the addition of the exponents. So let's go ahead and we'll do this very thing here for the two numbers that we just looked at. So these are our two numbers here. We have our x, which is minus 0.7, that's the top number, and our y, which is 492.75, that's the bottom number. So we know that whenever we multiply the two together, we multiply the Mantisses and we add the exponents. So let's look at the exponent first of all. So the exponent for the x, that is xe. Well, this number here, the first one is going to be the sign, and the next 8 are going to be the exponent. So if you look at this 0, 1, 1, 1, 1, 1, 1, 0, and you check that out and you change it into the decimal value, you get the decimal value 126. Of course, we're going to have to take away the bias, which is minus 127. So the exponent for x is going to be minus 1. Now we do the same for the y, and the y is going to give us 135. And we take away the 127, it'll give us a value of 8. So the exponent for x plus the exponent for y is minus 1 plus 8, so that's going to be a value of 7. So the final value for the exponent is going to be 2 to the power of 7. So that's relatively straightforward. Let's go ahead now and we'll multiply the Mantisses. So these are our two 32-bit numbers here that we're multiplying. The top one is our x and the bottom one is our y. Now we're interested in multiplying only the Mantissa, so the Mantissa starts at bit 10. So the first bit is the sign, and then the next 8 bits are the exponents, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So the Mantissa starts at this point here. So we're going to have 0, 1, 1, 0, 0, 1, 1 repeating for the first Mantissa, and that's it written here. Now remember that in order to do this, we're going to have the value of 1, which is understood at the front. So this is a normalized form. So the actual value that we're going to multiply will be 1 point, and then the Mantissa. So there's actually 24 bits here that we're going to multiply. Now the same thing goes for the next value. We have our sign, and then we have 1, 2, 3, 4, 5, 6, 7, 8 bits. So this bit here is the 10th bit, and this value here is going to be the 1, 1, 1, 0, 1, 1, 0, 0, 1, 1. But of course, again, it's a normalized form, so it's actually going to have a 1 in front of it, so it'll be 1 point, 1, 1, 1. So these are actually two 24-bit numbers. So let's go ahead and we'll multiply these. So in order to multiply these two numbers together, we do it the same way as we would if we're multiplying decimal numbers. So it's going to be 0 times the top line, and then you would come in 1, and it would be 0 times the top line again, and then you would come in 1, and 0 times the top line, and we would do that 13 times. Of course, we're not going to write them all down because they're all 0. But what we're going to do is we can count in 13 positions, and that's the 13 positions there. And the very first one that gets multiplied will be one more position in. So it's going to be 1 times everything above here. So we just take everything we have here and we copy it down here. And we do the same thing for the next one. We move 1 position in and we copy it in. And then the next two are zeros. So the next two are zeros. So the 1 position in for 1 0 and the second position in for the second 0. And then the next value is the 1, and we get copied over here. And we continue doing this all the way along until we get to the very last one. And that's all I've done here. So it's no different than you would do if you're multiplying together two decimal numbers. So now what we want to do is add these up. So again, there's nothing in the first 13 columns, so we could just put in a value of 0. So this is going to be 13 zeros here. And we have 1 here, so that's a 1. And you see I've drawn the lines down so it's easier to see. We'll have 1 plus 1, where 1 plus 1 is actually going to be 1 0 in binary. So it means that we're going to have 0 in this column here, and we would carry 1 into the next column. And again, we'd have 1 1, which whenever added up would give us a value of 1 0. So we'd have 0 in this column again, and we carry the 1 across, and then we'd be left with 1 in that column. And we continue doing this. So for example, 1 1 here will give us a 0, and we'll carry the 1. In this column here, we're going to have 1, 2, 3, 4, 5. Now 5 is going to be 1 0 1, so there will be a 1 here, there will be a 0 here, and we would carry 1 into this column. And then we would add this column up, and we would carry the values into this column, and so on and so forth all the way along. So this is just simple binary addition. So finally, whenever we've added all of those up and we've got all of the values, we could then try and find the position of the decimal point. Now you do this the same way as if you were multiplying together at two decimal numbers. We know that there's 23 values here after the decimal point here, and there's 23 values after the decimal point here. So there's going to be 46 places in until you get to the decimal point. So we start off here and we count in 46 places. And the 46th place is at this point here. So the answer we're going to get is 1 0 point in all of these numbers. And of course that's going to be times 2 to the power of 7. So this is our Mantissa and this is our exponent. Now what we're going to do is we're going to write it in a normalized form. So rather than have the decimal point here, we're going to shift the decimal point one position to the left. But whenever we push this one position to the left, we've got to change this from 2 to the power of 7 to 2 to the power of 8. So this here is the value for our Mantissa, and this here is the value of our exponent. So let's go ahead and we'll actually now figure out the final answer. So we know that we're going to multiply together a positive number and a negative number. So the answer is going to be negative. So it means that the sign bit is going to be a value of 1. And we've already worked out what the exponent is going to be if I run up here. So the exponent would finally be 2 to the power of 8. But 2 to the power of 8, but we've still got to add on their factor of 127. So this will finally give us the value of 135. Now 135 in binary is 100000111. So that's us got our sign and we've got our exponent. So now we've got to find the Mantissa. So just head up here again, we'll have another look at this. Now we know the Mantissa starts after the first decimal point. So after this decimal point here, we're going to count 23 digits. So it's going to start off 01011, and you can see that's what we've got down here, 01011. So we're going to count along the 23 bits, and we'll chop off what we have at the end. So that means we're going to have this value here for the Mantissa. So finally what we can do is we can put the sign and then the exponent and then the Mantissa, and we're going to get this value here. So this value here is exactly the same as the value we've seen whenever we do the multiplication in the tool. So that's the same as this value here, which gives us minus 344.924987792969. So I suggest that you open up the conversion tool and you check these numbers out and see that they all match and see that you understand how we went through this multiplication. Now don't worry too much if you didn't understand or follow all of it. We will be coming back to this video whenever we go and we build a floating point, a 32-bit floating point binary multiplier, which we'll get on to in a later video. So thank you for listening. I'll get you on the next video. Goodbye.